Alrighty, folks. Hello and welcome back. This is Stat 2602, second half of Lesson 9. This is our final lecture. That's it, that's all. Shouldn't be a long one. So picking up where we left off. Again, we have a time series. We've broken it into its three main components. We have trend, seasonal, and the remainder part to it. The question that we started asking last class is, does this remainder part have some sort of memory in there? So if I look at the difference between 2 points in time within a month period, does what happened a month ago impact what's happening now? What about 2 months ago, 3 months ago, so on and so forth? This memory that's hidden inside that remainder. So if there is no memory inside of there, then what we have is just white noise, which means trend, seasonality. This explains everything that we need to. But if there's things that's not captured in trend, if there's things not captured in the seasonality, if this memory of what happened beforehand does exist, we need to be able to model that. So we're going to be looking at different models this class. So three main ones: autoregressive moving average and a combination of the two, or autoregressive moving average model. And how do we decide which one we're going to use? All right. So first thing we need to talk about is residual error. So residual error is really just the difference between, well, what is the predicted value? What is the true value? What's the difference between the two? So sometimes positive, sometimes negative, but again, it's just the difference between the two. So we have residual errors for each one of the values in our time series, because once we build our model, we're able to predict and then figure out, well, what is the difference between these two things. Now, at the end of the day, if that residual error is just random noise, then again, what we've done is we've encapsulated everything that we want to in terms of our model. So if a model has accounted for all the serial correlation in the data, the residual series would be a series uncorrelated. So this is going to be the memory has been taken out completely. All we have left is that basic white noise. Why is this not switching over? Here we go, switch. So let's just define white noise. I believe I've mentioned it already. So we'll say a time series will index, or we'll use the notation W sub t this time around instead of X sub t. This is going to indicate we are dealing with discrete white noise. So if the variables W1 all the way up through Wn are independent and identically distributed with a mean of 0, again, what we have is white noise. Now, specifically, if this follows a normal distribution with a mean of 0 and a variance of sigma squared, then this is called a Gaussian white noise. All right, so what good looks like in terms of a model? For a well-specified final model, and that's what we're looking for here. So we have trend, we have the seasonality, and what we're looking for is that remainder, that randomness that we're trying to capture, that memory that we're trying to capture. The stochastic dynamics is what I have listed in the slide here, so that randomness overall. The residuals should be indistinguishable from white noise. So once we put everything together, and we have everything, again, what we should have is, again, just white noise with a mean of 0, no serial correlation. So if I do the AFC, the correlogram, what I should see is at lag 0, I have a value of 1, because if I'm comparing a time period to itself, again, it's perfectly correlated. But everything else afterwards, there should be no correlation inside of there. And roughly constant variance. Okay, so if the residuals show a pattern, then again, something has been left out. And then we have to go back and we have to refine the model at that point. So again, we check to make sure that we have everything covered using the ACF and the PACF. I haven't really talked about that too much. We'll talk about that in just a couple of slides. But those two characteristics, or those two corelograms that we get from there, we're going to use those to help us determine when we've reached the model that we want. We could also use the residual plots, again, making sure that there's no trend, no seasonality, no change in the spread of the data. But the ACF and PCF are good enough. So at the end of the day, again, we assess the model's adequacy by testing whether the residuals look like white noise. If they do, we've we've got everything inside of there. If not, something is missing and we have to go back to the drawing board. So a white noise series usually arises as a residual series after fitting an appropriate time series model. The correlogram generally provides sufficient evidence, provided the series is of reasonable length, to support the conjecture that the residuals are well approximated by white noise. So the only parameter for white noise series that we really need, like once we get down to that one point in time, is to really capture what the variance is going to be, that sigma squared. And of course, we can do this simply by just using the var function inside of R, because once I have that final white noise series in there, I can find out what its variance is, or estimate it based upon the data that we have. All right. So let's talk about specific models. All right, so x sub t is going to be a time series. X sub t is a random walk if the following property holds true. So if, I didn't lose my pen here, if x at time period t is equal to exactly what it was the time before. Now remember, for forecasting, we had the naive forecast, which was simply just saying, I'm only going to take what happened the last time around, and that's going to be my prediction for this time around. What we're doing here is exactly the same thing, except for each individual time, we're just adding on a little bit of white noise. So a little bit of an error we're tossing on there. Again, W sub t is the white noise series, so this has a mean of 0 and some variance of sigma squared. All right, so in this setup, again, x sub t is equal to x sub t minus 1 plus wt. I can perform backward substitution. What I mean by that is I could take x sub t minus 1 and rewrite this as, well, I go one step back, so this is t minus 2 minus the white noise at t minus 1. I could do this repeatedly, go, okay, well, for x t minus 2, this is equal to x t minus 3 plus the white noise at t minus 2. And if I go on and on and on, there's going to be a point where we eventually stop, but I can rewrite this whole thing as x sub t is equal to just the white noise at period 1, the white noise at period 2, all the way up to some white noise at period time t. So one thing to kind of note here is back substitution is used to define more complex time series models. It also helps us derive second order properties. So when we're talking about the mean and autocovariance functions, we're not going to spend too much time doing that at all, but it's just something that is good to bring up. Now this is kind of coming from a little bit more of a theory side of things. I want to quickly introduce it, but I don't want to spend too much time talking about this. So the backward shift operator. So the backward shift operator, we'll define this as B, does the following. So this performs an operation on a time series at time t. It just brings it back one spot. So B applied to x sub t gives us xt minus 1. So that's all it does. It takes a point in time and shifts it back by 1 unit. Now we can apply this backward shift operator multiple times, or I could say n times in total. So applying b n times takes x sub t to x sub t minus n. Okay. Why is this helpful to us? Well, for one, I could rewrite the series using backward shift operators and put everything at exactly the same time period. Why is this going to be useful? We'll show you in just a couple of seconds here. So again, definition of the random walk, x sub t is equal to the time period right before plus some wt. Now, one of the things I could do is, again, I know that b at xt, this is equal to, again, I'm applying that backward shift operator on x at time t. It brings it back one spot, so this is x t minus 1. So again, I could rewrite this x t minus 1 as this b x of t, which is exactly what we've done right here. Now, let's suppose I wanted to have all of my x's on one side and then my white noise on the other side, so I'm going to just bring that over here. So again, that's positive here, so it becomes negative here. Now I have x sub t in both of my terms, so I can factor that out. I'm left with 1 minus b x of t. Now again, b is a backward shift operator, but let's think of this as I could write this kind of like a variable. So I have a function in terms of this backward shift operator, so I'm going to call this theta of b. And in this case, that is just 1 minus b in this case. So some function of b applied to x of t, and this is going to equal w sub t. Now, why is this useful sometimes? Well, it's useful in the following way. So again, one of the things that we wanted to be able to talk about is when a time series is stationary, and we can approximate, again, that autocovariance. We can approximate the auto mean, or the mean function in this case. But again, it needs to be stationary. So how do we determine when things are going to be stationary? Well, we can kind of look at this function. So again, b is a backward shift operator. If we treat it like a variable, and typically this is where we would do a substitution, I'd say instead of b, let's call this z, and then we're going to perform this on the unit circle, but let's just keep it as b for now. Or for the entire class, I should say. Let's just say I have a function in terms of b. I set that, or I have an equation in terms of b. Let's say I set that equal to 0, and I'm asking, where are the roots? So what values of b can I plug in that give me a 0 in my equation? Again, it is an operator, but we're treating it like a variable right now. So here's the theory kind of all wrapped up quickly. The roots of this characteristic equation, which is this equation here, so the equation in terms of, or the function in terms of b that gives us, we're setting that equal to 0 gives us the characteristic equation. So if we look at the roots of this, if they all exceed unity, so if they are all greater than 1 in terms of absolute value, so it could be greater than positive 1, less than negative 1. It can't be 1 or negative 1 or anything smaller or in between there. But if it's outside of that range, so absolute value greater than 1, then what we say is this process or this time series is stationary. So for a random walk, again, x sub t is equal to t minus 1 plus some white noise. This operator, again, rewritten as a polynomial, gives us 1 minus b. When I set that equal to 0, well, what values of b can I plug in that give me a 0? The only one that I can plug in here, well, to get rid of a 1, I have to have a negative 1, so b has to be 1. So if b is 1, well, that's not greater than 1 in terms of absolute value, so this is not stationary. So we can easily tell in this case when something is stationary and when it's not stationary. Now, when I do have a random walk, here's one interesting thing that we can do. We can build a new time series that is in fact stationary. So let's consider a first order difference. And by first order difference, all I'm simply saying is, let's look what happens when I just subtract a time series at t minus t minus 1. So if I look at 2 consecutive times and I subtract that, what do I have left? I have left is just white noise. So I can build a time series, a new time series, just by differencing out consecutive time periods, and all I should have left is just white noise. So building this new time series, we'll call this y sub t. This will be equal to delta of t, which is just the difference between x at time t and t minus 1. So if I have something that is a random walk, I can tell when it's a random walk by just differencing it out. And it should difference out to something that is just going to be white noise. And again, I can test this using the ACF function. I should have that lag of 1, lag 0 is going to be 1, and then everything else should be that white noise. Okay, so that's kind of like our starting point. Again, just taking what we had before and just adding something on. But let's get a little bit more complex than that. So what we're going to talk about here is autoregressive models, which is actually kind of that random walk was just a special case of this. So autoregressive models are as follows. So we have a time series, x sub t. We say this is autoregressive, an autoregressive process of order p, which we can write as ARP, if the following is true. So if x sub t, so a time period t, this is based upon information at the time previous to that and the time previous to that, all the way up for a total of p periods. And the relevance that we're taking from each one is defined by this alpha. So I have an alpha 1, alpha 2, all the way up to alpha p. So alpha 1 dictates, well, how important is, or what am I taking from that time period that just came before? Alpha 2, well, time periods 2 before that. All the way up to alpha p, well, what happens from p periods before that? So again, memory that carries on. And of course, at the end, what we have left is just that kind of white noise at w sub t. Now, key part here, obviously, if this is something of order p, ARP can't be 0, because if this was 0, then I wouldn't have a degree or order p equation. Now, in backward shift notation, again, I can take each one of these and rewrite this. So this is xt minus 1. I could rewrite this as b xt. T minus 2, I could write this as b squared x sub t, because it takes x sub t, brings it back 2 spots by applying that backward shift operator twice, all the way up to bp xt, which again takes xt and brings it back those spots. So I can rewrite all of this in terms of my x's. I can bring them all to the other side. So this would be xt minus alpha 1 b xt minus alpha 2 b squared xt minus minus alpha p b p xt, and this would be equal to wt. And now I can factor out the xt for each one of these, which would just leave me with 1 minus alpha 1, b minus alpha 2, b squared minus minus alpha p bp xt, and that's wt, which is, again, is what I have exactly right here. So I don't know why I wrote that, but I did anyways. There we go. And so this is equal to, it'd be, which is 1 minus alpha 1 b minus alpha 2 b squared minus minus alpha p b p. And if I set this equal to 0, if all of the roots are greater than 1 in terms of absolute value, then what do we have? We have something that is stationary, and if not, it's non-stationary. All right. So the question is, well, how do we tell if I'm dealing with a time series that is based upon an autoregressive model? So again, we're getting information from past observations. Now, when I look at the autocorrelation function, I'm going to notice that, yes, if I have an autoregressive model, well, it is taking information from time periods previous to that. So if I look at lag 1, okay, there might be information in there. Lag 2, okay, might be information in there. Lag 3 might be information into there. But there's a lot of confusion or a lot of carryover from what's happening. So how do we tell when we stop carrying over this bits of information? Well, this is where we get into this partial autocorrelation. So a partial autocorrelation at lag k is the correlation that results after removing the effects of any correlations due to terms at shorter lags. So if I'm trying to calculate lag of 1, perfect. I'm just looking, what is the correlation between now and one time period into the future? When I go to lag 2, well, lag 2 is going to contain information about, what happened from one period, because again, I know that, for 2 periods, I'm going to have information in there. But I want to know, well, again, what is the real amount that I'm getting from two periods beforehand? So if I could remove, when I'm trying to calculate 2, what I already know about 1, well, I can get a more better read as to what were happening for 2, and same with 3. When I try and calculate 3, I know there's bits from 1, I know there's bits from 2. If I could remove those, I can get a more truer value for what's happening for 3. So that's what this partial autocorrelation does. For each one of my legs, it kind of removes everything that I know previous to that. Well, in kind of a hand-wavy sort of way. So looking at this partial autocorrelation, if I'm dealing with an AR process, once I hit that order P, I should see something up to leg P, and then after that, it should just stop. I'm not taking any more information past that point in time. So we say in general here, the partial autocorrelation at leg K is the kth coefficient of an ARK model. Again, if the underlying process is an ARP, and K is greater than P, so if I'm trying to find, well, what is the coefficient at leg K, but I'm past an order P model, well, I stop contributing at that point in time, so those values should just be 0. Okay. So the plot of the estimated partial autocorrelations can be useful when determining the order of a suitable AR process for a time series. Now, the function we use is PACF, so not just ACF, it's the PACF. It's going to get us that. So again, it'll get us a correlogram. We'll read it in the same way, except we're dealing with partial autocorrelations instead of just the autocorrelation. All right, so specifically an AR1 function. So after we remove trend and seasonality, the leftover remainder or the wiggle often has momentum. So a high residual month nudges the next month up, but after the effects fade. So how do we model that? I'm going to take my time period T, and I'm going to say it's going to come from the previous from that. Well, how much effect is going to come from the previous of that alpha? And then again, we have some error, and if there's special properties of alpha, then that error is just white noise. So we say alpha is the memory. How much of last period carries over? And the way I want to think about this is, again, if I apply this over and over and over, so we get farther and farther away from that time period, we're just multiplying it by alpha. So the farther I get away is, well, it's just alpha what happened the time period previous to that. And then it's alpha the time period previous to that. And it's alpha the time period previous to that. So I'm just applying alpha over and over again k times. So if alpha is less than 1, well, what are we going to expect to see happen? Well, if I'm raising it to a power k, something that's less than 1 to the power of k is just going to keep getting smaller and smaller and smaller and smaller and smaller. So it's going to eventually die off. So that's basically what we're talking about here. And how quickly it dies off is really depending on the value of alpha. All right, so how do we tell when we're dealing with an AR1 model? Well, I'm looking at the ACF. Again, if memory is carried over, what I should see is an ACF that is going to be decreasing. So it's going to tail off eventually, but it's going to be a smooth decrease down. Now the PACF, what we should see is at lag of 1, there should be a big spike, and then everything else afterwards should be a 0 because all the information has already been used in that first leg. So just when we're talking about this alpha here, so if alpha is, say, 0.6, then what we say is 60% of, again, if we're talking about time periods within a month jump, and which is what we've been doing up with this example, if alpha is 0.6, that means about 60% of last month's kind of surprise carries over into this month. So whatever happened last month, 60% of that carries over into this month. When alpha is approximately 0. Well, what does that mean? Very little memory is carried over. So the smaller that value is, the less information, or the less importance of what kind of surprises happened from last month carry over into this month. When we are dealing with something less than 0, so what do we mean in this sort of case? Well, you can think of it as a high month might often lead to a low month afterwards. So if we have just a surprise amount of sales one month, well, what happens the next month? Or if we're running some kind of a promo one month, well, what's happening the next month? Well, then we might not get anything from there. Or we might get less from there. Oops, why is this not changing over? Change over. There we go. So again, in terms of stationary, so an AR1 model, t is equal to alpha xt minus 1 plus some error term et. Writing this in the backward shift notation, this is xt minus alpha b xt is equal to et, which means I can rewrite this as 1 minus alpha b xt is equal to et. So we look at when is 1 minus alpha b equal to 0. So what are the values of b that I can plug in? Well, it's going to be dependent on what alpha is. So if alpha is greater than 1, so if alpha was 2, remember, alpha times beta has to be 1 because 1 minus 1 gives us 0. So I need to be able to cancel alpha out. So if alpha is greater than 1, to be able to cancel it, I need to divide by that same amount. So if it's greater than 1, b is just 1 over alpha, which is less than 1. Okay, if it's less than 1, if b is less than 1, well, we have something that is non-stationary because it has to be greater than 1 for it to be stationary. So on the other hand, if alpha or do I have this backwards? Yeah, no. If alpha less than 1, there we go, then b is still 1 over alpha. But if alpha is less than 1, this gives us something greater than 1, which is exactly what I have here. So if the absolute value of alpha 1 is less than 1, then what does that mean? Again, that means that I'm going to get a b that is greater than 1, and thus, by our definition, is stationary. So I can quickly see, depending on what alpha is, I can quickly see when an AR1 model is in fact stationary. So if I look at the first couple here, or I have 3 examples here, and I'm asking, well, when are the following stationary? So I just have that time period t is equal to what happened right before it, multiplying it by 0.6, and plus some little bit of noise, which I'm in this case, I don't know why I call this a sub t, but yeah. So is this stationary or non-stationary? Well, I look at my alpha. My alpha is 0.6. That's less than 1, so therefore this is stationary. Well, what about my next one? My next one, x sub t. I have t minus 1. I'm multiplying that by 0.99. Okay, so that's less than 1. But I have this 50, and I have at. Well, I know at is fine. That's my randomness. What about that 50, though? Well, I can think of it as I'm just shifting that randomness by 50. Okay. Doesn't change anything. It's still, in this case, dependent completely on what is my alpha. My alpha in this case is 0.99, stationary. What about for my next one? Well, obviously 1.2, that's greater than 1, so this is not stationary. So by simple examination of an AR1 model, it's easy to determine whether it describes a stationary process. Again, for higher order models, stationary, there's not a quick, easy way of being able to do this. I have to look at, well, what are the roots of the polynomial? Again, when I'm dealing with b as a variable. Now in R, I can use the polyroot function, so I can build that polynomial that I get from applying that backward shift operator. I can ask, well, what are the roots? And if all of the roots are greater than 1 in terms of absolute value, then perfect, I'm done. That's it, that's all. All right, so let's jump back into R. Let's play around with this example for a little bit here. All right, so just a quick recap here. Remember what we did. Let's replot this. So we built a time series. And how did we build? Well, actually, let's recap a lot more here. Let's go back up to the very top. So we built a time series starting in 2017 on the January 1st, and we built 96 months out. It had a trend. So that trend was 600 plus 4t. 4 was the slope, intercept 600. We had a seasonal vector here. The seasonal vector was minus 80, minus 40, 10, 20, 30, so on and so forth. So we saw a dip at the very beginning of the year, and we saw an increase towards the very end of the year. We repeated this vector a total of 96 times, or sorry, for a total length of 96 times. Now there was a couple of promos. So we had a couple of months where there was just a big push for things. And then we had a couple of negative stocks, so supply disruptions. And again, I think that was around the COVID time, so it seems reasonable to throw those in for 2 months. And then we wanted to put some memory into here. And we didn't really describe this. We will in a little bit. But we have an autoregressive side of things. So we've talked about that autoregressive, which again is just taking something that happened in the time period beforehand. So we're putting this AR as an AR1 with 0.5. Now it has an MA in there. We'll talk about that in just a sec, what exactly that means. But for now, there is an autoregressive and a moving average component to the residuals or the remainder in there. And then we put everything together. So we had the trend, we had the seasonal component, we had the promo, the shock, and the remainder. So that gave us this time series here. So this is the original, our trend, our seasonal component, and the remainder. This is what we're trying to model. So we decompose this. R sub t is the remainder. Let's do ACF of, no, I want to do, let's just do it here. ACF of the remainder RT, right? There we go. Okay, so what does this tell us when I use that ACF function? Well, at lag 0 is a 1, okay, but what happens afterwards? So we have something at lag 1. So memory is carried over from the last period around. Well, at lag 2, nothing really is happening there. Lag 3, I have something that's negative. Lag 4, negative. Lag 5, negative. Lag 6, positive, positive. So there is information that is being carried around. So because there is memory in there, let's try and model this. So maybe it's just a simple model. Maybe it's only information from one step previous. So I could use, or I could try and fit an AR1 model. And that's what I'm going to do first here. So I'm going to call inside of, or I'm going to use the ARIMA function. And I'm going to store this in a variable fit underscore AR1. And I'm just going to build an order 1 model. If I summarize this, it tells me my coefficient for my AR1 model is 0.4994. So basically it's 0.5. Well, if we look at the original data here, my AR1 model was a 0.5. Okay, so maybe it got close. Maybe I've got everything in here. Well, let's do an ACF, fit AR1, and I want the residuals. Right? Because if the AR1 process was enough, I'm using that to model everything else. Well, the residuals, the leftovers, when I take the remainder minus that new AR1 model, the residuals, if everything has been found in there, should be white noise. So if I run this here, okay, lag at 0 is 1. That's perfectly fine. Things that come afterwards, okay, well, lag of 1, that seems to be in between the blue lines. So maybe that's not statistically significant. Lag 2, nothing. Lag 3, ooh, we're starting to see some things in here. So there is information that I have in here that hasn't been accurately accounted for. So maybe an AR1 model is not good enough. Well, maybe I need a higher order model. Maybe instead of going just 1 month previous, I need to go 3 months previous. So let's build an AR3 model. So in this AR3 model, my AR1, my first coefficient, is 0.62. My AR2, so the second coefficient, what I'm taking from 2 periods in, is negative 0.2567. So I have this kind of like a correction. 3 periods, again, negative 0.1901. So I see a big boost from the time period previous, but whatever happened in the second and third, well, I'm taking negatives of that. So it's kind of undoing what we have happened there. I do an ACF based upon this model. Oh, we've got almost everything now. So notice here, again, I have in between my blue lines almost everything except for, I'm at lag 1, 2, 3, 4, 5, 6, 7. 7 lags in. I still have something in there. Now, that one lag, it is past the blue line. Not by much, though. Not by much at all. So I might just write that one off. Or I can keep trying. I can keep going up to higher models. Let's try an AR4. I have my coefficients from there. I'm not going to read through all of them again. ACF. Okay, now it looks like everything is inside of there. So maybe an order 4 was good enough to be able to capture everything. But we know for a fact that the original model was only in order 1. Order 4, okay, well, maybe I've got enough stuff. But the question is, well, can I do better? Now, one of the things we can do here, I tried an AR1, AR3, AR4. Well, let's say I want to max out at AR5, but I don't want to try each one of these. I want to automate this process. I can use the AutoArima function or auto.arima function and say I want a max p-value of 5. I'm going to set QE is equal to 0 because, again, we're going to get into that moving average part of things, but I don't want to include them just yet, and I don't want a seasonal component in this. So if I do this, I run this function. It's done. Let's do the summary of this. It gets me an order 4 model. And notice here, let me just bring this up a bit. My coefficients are exactly the same. 0.5582, negative 0.3405, positive 0.0139, and negative 0.3259. So it found exactly the same model, but again, I didn't need to do the trial and error to be able to get to an order 4 model. I just say, I want at max an order 5. You find me the best model that does this, and that's exactly what it did. So it found me an order 4. But the question now is, maybe an autoregressive is I need more than that in there. Because, again, autoregressive, what is it doing? It's looking at, well, what happened at the time period previous? I'm going to take a portion of that and continue onwards. Let me just switch up here. But let's talk about a moving average model instead, an MAQ. So this is not so much momentum. This is more talking about echoes and recent shocks. So say when a promotion or an outage cause short-term ripples, things that we can't predict because they're not going to happen all the time. Like a promo will run every once in a while. There might be a shortage of stock at some points in time, but this is not something that goes on for long periods. But there is an effect to what happens here. So when we have these short-term ripples, these errors, not based upon past values, but just surprises that kind of randomly happen in there, we need a different way of being able to model this. So we say today's value is a weighted sum of recent surprises. So again, these could be promos that we've done or outages. There we go. And again, it's the one-off sort of things here. not in terms of the autoregressive, where it's really what we did last month is going to help us or hurt us to what we're doing in months previous. This is kind of what, hey, if a surprise happens in this period, this surprise is going to carry on for a little bit, but it's not going to be a normal sort of thing. And it's not based upon what happened last time. It's based upon just an error or surprise that happened last time. So when we look at the model of this, x sub t is equal to this error, this e sub t, plus the error of time previous, the area of time previous before that, if we're talking about an order p, all the way up to p periods before that. And each of these kind of like little bit of surprises that happened at the other time, we're taking theta of that. Not alpha, theta of that. So some level of importance. So how do we spot these ones? Well, when we're dealing with an AR process, we looked at the PACF. That was kind of the big one there, that PACF. Once I removed all of the redundant information for the time previous, if I get to a lag and no more information is being used, well, that tells me where I'm dealing with, what order I should be playing around with. But not so much here. Because we're talking about not things based upon the last time around, but the error, those weird sort of one-off ripples that we're going to get, we can just use that ACF to be able to help us figure this out. So when we have sharp cutoffs on the ACF after a specific lag, this is indicating, this is telling us that we need a moving average model. The PACF, what's going to happen there? It's going to tail off, or it might oscillate. So again, it's not going to be a quick dying off at this point in time. We'll see a quick jump in terms of Q, but we'll see an oscillation up to that point for the PACF. So the larger Q is, think of it as the longer shock tail that has happened here. So if, it's in order 1, tells us that, whatever happened last month, or a surprise that happened last month, is only going to affect this month, and it's not going to carry on past that point in time. But the longer Q is, the longer that effect has into play. So if it's an outage of product or something along those lines, and we have an order Q model representing that, well, that's going to take Q periods to be able to self-correct. So let's go back to R. And let's just go just want to reprint off here the ACF and the PACF for our remainder. So looking at the PACF, I do have things that kind of oscillate here. So it goes up, then it goes down, then it's kind of going back up here. We don't really know. It looks like everything else is dying down in there. Kind of a clear cutoff after leg 1, 2, 3, 4, 5, 6, 7. But we do have some values in between these ones that really just don't play a role. They're not really all that statistically significant here. So this is not really kind of pointing directly to an AR model. Well, what happens here? Is there a clear cutoff? Well, not necessarily either on this one. It does seem like after this point in time, there is a cutoff. This is over a year into the future here. So maybe a moving average is kind of appropriate. So I can do the different AR models here, but I can use the auto ARIMA function again. This time I want an MA model, so I'm going to set P is equal to 0, and I'm going to set Q. How many periods do I need? I want to set a maximum being 5. And if I do this, it's already built the model. It gives me an order 5 model. And if I plot the residuals of this, same idea in this one. Even for an order 5, I still have a little bit of what's happening here. So it's not exactly white noise. There does look like something is kind of carried on. So an order 4 AR model seems to do everything well for the residuals. This seems to do something relatively okay for the residuals. There is a little bit of a nudge here, and again, it's just a little bit of a nudge. So maybe this is good enough. But we do know, based upon the data that we created, because we simulated our time series data, is we know that there's shocks and there's shocks in there because we added promos, we added supply chain issues, but we also had memory in there based upon an autoregressive and a moving average model. So what happens again if we can combine both those together? There we go. So we have an autoregressive moving average model on parameters P and Q. So think of this as a mixed momentum and shock memory. So momentum, things that happened in previous months, is going to help us build on this, but it's also taking into account these the surprises that could have happened in a specific month. So a promo or supply chain issues or something along those lines. So many series show both some inertia in the level. So again, yesterday influences today, and after effects of shock. So think web sessions after a sustained campaign. Part of that is going to be persistence. So part of that's going to be an AR, but part of that campaign is going to be a shock tail. So we need a moving average aspect to it. So an ARMA blends both of those models into one. And basically all we're doing is we're taking both and we're just merging them in. So there's going to be a whack of different parameters inside of here. So the AR part, which is the first part here. So this is our autoregressive part. This is our moving average. So this is AR. This is MA. So the AR part, this part remembers recent levels. So what happened last time around at X sub T minus 1? Again, I'm taking some alpha of T minus, or of that, however far back we go, that level of importance into it. And this is, again, shocks fade gradually, geometric like. The MA part, this series remembers recent surprises, so shocks add short tails. And again, together, gives us a flexible short-term dynamic without over-differencing. So how do we spot this? Now this kind of fits more into what the ACF and PCAF of show. Both of them tail off, but there is no clear-cut sort of cutoff here. So again, going back to R, I jump back here to my last picture, and let's make this a little bit bigger here. When the ACF, again, I don't have a clear cutoff. I see a decrease, an increase, a decrease, and then eventually here maybe, but we don't know really what happens over here. It's tailing off, but it's not really cutting off. And same idea with the PACF. I have an increase, decrease, an increase. Again, it looks like everything kind of tails off afterwards, but did it really tail off here or did it tail off here? Again, it's not kind of a clear cut on this. So this is kind of giving us the indication that a mixed model is ideal. Again, if we saw this tail off and there was a clear cut on the ACF, that would tell us that I'm dealing with a moving average. If the ACF tailed off and the PACF had a clear cutoff, that would tell me that I'm dealing with an autoregressive model. Since both aren't doing either of that, they're both kind of tailing off, a combination of the two would seem appropriate at this point in time. So kind of a rule of thumb, we don't, like, unless the data is really pointing us towards it, we try and keep the orders relatively small for both. So what I'm going to do here is I'm going to fit a max P and a max Q of 3. So I'm going to say I don't want more of an order 3 autoregressive portion, and I don't want an order 3 for a moving average portion. Now, stepwise and approximation, I'm setting these equal to false. These are just ways of being able to speed up this algorithm. Sometimes this is going to take a little bit of time depending on the level of, or the data that we are dealing with in the order that we're potentially dealing with here. Since I'm dealing with a max P and a max Q of 3, I'm not going to do any kind of approximation on this one. So I'm going to run this, and again, this is going to take a couple of seconds to do. More than a couple of seconds. We're getting there. Well, let's jump back for a second as this is working through. And my final slide, and I'll go back. Oh, it's already done. I'll go back in a second. So just kind of recapping on things I've already talked about here. So choosing an MA versus AR versus ARMA. Again, if the PCAF cuts off, ACF tails, we're talking about an AR function. If the ACF cuts off and the PACF tails off, then I'm talking about a moving average function or moving average model. And if they both kind of just tail off, then I'm talking about a mixed model here. And again, practical tips, keeping P and Q small unless the data really insists. All right, let's go back to the data here. That was my last slide. That's all I need for this one here. This is done, so let's do a summary of this. So this is found in AR2 model. So my coefficients are 1.32, negative 0.9265. In terms of my moving average, this is found in order 3. So I got a negative 0.7576, a 0.2428, and a 0.2898. So in order 2, order 3, putting it together. So it uses the max of the moving average, but it used only in order 2 for an autoregressive part of this. Let's look at the residuals on the ACF. All right. Everything after that very first lag, which we know is going to be 1, so that's lag of 0. Everything else is between the blue lines and very, very much in between those blue lines. So it does look like the residuals at this point is white noise. So based upon the remainder of what we had, I can model that remainder as an order 2 autoregressive and order 3 moving average, put them together, and that's exactly what I have here. All right, so I've created this model. Now remember when we started this, let's go back here in my slides just for a second. The very first slide that we were talking about. So you're an analytics lead at Shopko, an e-commerce retailer. Management needs a 12-month revenue forecast. So we want to be able to forecast 12 months into the future. Well, let's do that now. So we've decomposed this into a trend, into a seasonality, and we looked at that remainder. We saw, okay, there was memory in there. How do we model that? We're using an an ARMA model of order 2, 3. That covers everything. The residuals of that are white noise. So now let's put this all together. So what I want to do is I want to use the forecast function. And I'm going to forecast. I'm going to take this fit underscore R. This is my ARMA model. And I'm going to predict 12 months into the future. And I'm going to store this in F sub R. Okay, so I've taken that remainder, that memory, and I projected that memory 12 months into the future. Now I need to take trend and I need to take seasonality. Okay, so what I want to do now is I have my trend data. I want to find a line of best fit for that. So I want to build a model. I'm not using the LM function, I'm using the TSLM, so it's going to be a linear model from a time series. Now, this is the important part. I'm saying the decomposition, which we put in the vector name TT, this is explained by trend. Now, trend is your indexing vector here. I don't have a vector named trend. I have trend underscore sim for the simulation part of things, but I don't have trend in here. So this is based upon the TLS or TS part of the LM function here. And it's just going to, again, take the vector TT, the decomposition into the trend, and use the, it's going to take the decomposition of the trend from the time series and again model it using the trend special notation here. There we go. And if I look at this, now remember the original model for the trend simulation in the original model for what we built here had an intercept of 600 and a slope of 4. This took that data and estimated the intercept at 632, so very close to 600, and 3.625, again, very close to 4. Now let's project this 12 units into the future. So I'm creating another vector here, 12 units into the future. Done. And now, so I have a 12-month projection for the trend. I have a remainder 12 months predicted in the future. There we go. The last thing I need is the seasonality component of to this. And all I'm going to do is, again, I have my seasonal vector, my decomposition into my seasonal vector. I'm just going to take, and this is what I'm doing here, I'm just taking the last 12 months of that seasonal vector, and that's going to be my new 12-month projection into the future. So putting this all together, I'm going to take the average outcome for, again, the future values predicted 12 months into the future. I'm taking that future vector or the seasonal vector that was just created, and again, the forecasting for the remainder, putting that all into final. Now, if I look at my original time series data and what we just created here, and I'll plot this in just a second. Notice that when we start off in January, we see an increase in February, March, April, all the increases into the end of the year up to December, 922. And then what happens at the beginning of the January of the next year? We see a decrease, 683. So there's always this build up. There's some fluctuation. Sometimes it's going up, like we get to July to August. From July in the first year is 624, August 575. So there is a drop that happens inside of there. So there is some fluctuations that are going. But again, the same idea. Once we get to December, then we're going to see a big drop from there. So I got all the way up to December on my very last year of 2024. That was 1,091 and change. So what's January of our predicted for 2025? Well, that's 852. So again, we saw that drop. And we're seeing increases, and some drops along the way. And then we're going to see in December 1,186. So again, it's increases. Does this follow? Well, let's plot this. Oh. There we go. All right, and we see in the graph here, the red is the predicted new values, that final forecast. So starting in my first year, again, we see an increase, decrease, increase. Start of the second year, boom, big drop down. And a little bit of bad things are happening here, but then we see an increase, and then next year, drop down. And again, some fluctuations, an increase, drop down. So what's happening here? Well, again, a little bit of fluctuations, not by much, but we see an increase. What happens after that increase? Drop down. But we're seeing an increase at the start of every January. So from this to the next year, which is here, we saw an increase. Well, here we actually saw a decrease, but then we see an increase, 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 increase every single year. So there was one year that was a little bit off over that. But again, same idea. We see an increase from when we start the new year. We have some up and downs which are projected, and then a dramatic increase towards the end of the year. So by the look of it, again, this is kind of following exactly what's happening from the periods before. So it looks like everything is really being encapsulated here. So that's it. That answers the original problem that we had. We want to be able to predict to the years into the future. So we already knew from the last lecture how to decompose things in terms of trend, in terms of seasonality. What we did here is really just looking at that remainder part, really focusing on that memory. What is carried over from time period to time period? Is it specifically coming from the last month? So are we talking about an autoregressive function where it's specifically what happened in that month and we're carrying that over? Are we talking about a moving average, which is kind of like the surprises that happened from that last month? How much importance do those play and how quickly do those die off, or a combination of the two? So that's it. That's all. That's the course in a nutshell. If you have any questions, comments, concerns, that was a little bit longer than I was expecting for today, but that wraps up everything. So if you have any questions, comments, concerns, feel free to reach out. You have all the information now to do all of the assignments. Yeah, that's it. That's all. We'll see you. I wouldn't say see you the next time. We'll see you at the final exam. Until then.